Hello everyone, and welcome to the second video on Riemann sums. In this video, we're going to go a little bit further and discuss the limit of Riemann sums. In terms of area estimation, you'll remember that we've seen how Riemann sums can be used to estimate the area that lies between the x-axis and a continuous positive function y equals f of x, all the time remaining within an interval a to b. We're going to use areas of n approximating rectangles. In short, the procedure to accomplish this was presented as follows. We were told to compute delta x by calculating b minus a over n. This would be the base of each of the rectangles and also the width of the subintervals themselves. Then we had to select xk arbitrary points within each of the n subintervals of AB, which themselves ranged from a to a plus delta x, and then from a plus delta x to a plus 2 delta x, and so forth. So basically we have n rectangles or n subintervals of width delta x that are listed in this description. Then for each of the xk's that we selected arbitrarily, we had to find the function's value for the corresponding xk. Or equivalently, this meant finding the height of each of the k rectangles. And then we estimated the area by adding the area of each of these n rectangles. F of x1 delta x would be the area of the first rectangle based on a height corresponding to the function's value above x1, and then so forth for the second and eventually to the nth. Equivalently, we could write that the area is roughly equal to the sum, so a summation, of all rectangles from k equals 1 to n, whose heights are f calculated at xk and whose base are delta x. So here we're using sigma notation in order to present the exact same addition that is presented at the top of the slide. Most of all, we have described how an improved estimation of area is obtained when the number of rectangles increases, and as a result, as the width of the subintervals themselves decrease. This was observed regardless of the points xk that were chosen within each of the subintervals, which brings us to a very important fact. And here are limits of Riemann sums. The area that lies between the x-axis and a continuous positive function y equals f of x over an interval a to b is equal to the limit as n goes to infinity of the sum of f of xk times delta x, regardless of the points that are selected within each of the subintervals. So essentially, the decision to pick left or right or midpoints of each subinterval is no longer necessary because in the end, the limit process where subdivisions grow to infinity will remove all estimation errors. So here's a procedure that we can use to find the exact area that lies between the x-axis and a positive function f of x over the interval a to b. First of all, we're going to compute delta x, the width of each subinterval, by calculating b minus a over n, but this time n will remain unspecified. We will not replace n by 4 or 8 or 12, but rather leave it as a variable. For convenience, we're always going to select the right-hand points of each of the subintervals. So I've listed the subintervals here, and as you can tell, the right-hand point, a plus delta x in the first subinterval, a plus 2 delta x in the second, a plus 3 delta x in the third. There's a pattern there where xk, the kth right-hand point, is always obtained at a plus k delta x's. Then we're going to find a general expression for the function at point xk, or equivalently, this will become the height of the kth rectangle. So this is our three-step setup, and we have everything we need now to calculate at least an estimation of the area at first. Okay, so we're going to find a general expression for the finite sum where we have calculated f of xk, the height of the rectangles, delta x, their width, and we're ready to do the addition of all of these areas. This is still imperfect because n has not been specified, but it will become perfect once we finish this off with a limit that forces n to infinity. So an infinite amount of rectangles will have been produced. The estimation areas will have been minimized and become 0, and we will get the perfect area. Let's put this in practice. We're going to find the exact area that is bounded between the parabola minus x squared plus 6x plus 1 and the x-axis, staying within the bounds 0 to 4 using a limit of Riemann sums. This is the same function that we estimated with a finite number of rectangles in our previous slideshow. Okay, so this time 4 minus 0 is b minus a divided by n to create n rectangles. This would be the width of each of these subdivisions or of each of the rectangle's bases. Notice how n is left as a variable. So we're not specifying yet how wide each of the rectangles are. According to our setup, a plus k delta x will always be the right-hand point of the kth rectangle. So with an a value of 0 in this example, and k times 4 over n as the delta x, we find that xk is 4 over n times k. Our function's rule is to square the x value, subtract it, and add 6 times the x value plus 1. So applying this rule to xk minus xk squared plus 6xk plus 1, we're ready to replace the expression we have for xk found in the previous step. And because we're squaring the 4, the k, and the n, and I distributed for the second term the 6 times 4 is 24, and we have 1 as a constant. So this last expression, f of xk, represents the height of each of the rectangles, where delta x equals 4 over n is the width of each of the rectangles. So we're set. We're now going to do the addition of the area of each of the k rectangles or each of the n rectangles that we have. So notice in the square parentheses that the expression I'm using is the one we found previously for f of xk. Those are the rectangle's heights. Delta x is 4 over n. It's a little bit of algebra now. We can distribute 4 over n to each of the terms. So remember that when you distribute numbers combined with numbers, n's combined with n's, that explains the changing exponents to the n's and the changing coefficients, but there are no new k's multiplying with the ones that were there, so the powers of k have stayed the same. Properties of summations allow us to split terms of a summation that are added into individual sums of summations. And we can even remove constants from the summations. In this case, since the summation variable is k, anything that is not a k, that includes constants like 64 and n's, are considered as constants with respect to the sum and can be removed. Now in red, I've highlighted the 3 series that perhaps strike a bell or ring a bell. Those are summations for which we have established rules in the past. We have formulas to calculate these sums. In fact, for the sum of k squares, n plus 1, 2n plus 1 over 6 was the formula we had established. For the sums of k's, n plus 1 over 2. And in the last one, since we're adding 1's and there are n of them, well, we simply have n times 1. Now here's a neat trick, because remember, we're going to do a limit eventually. So notice how numbers 64 over 6 and 96 over 2 and 4 can be reduced or simplified. So I've collected the numbers together in each of the fractions, And at the denominator, I've split up the powers of n and shared them amongst the different terms that involve n's at the numerator. So n cubed, I'd written as n times n times n, and shared with the numerator's expression, n plus 1, 2n plus 1. I've done the same for the second fraction, so n squared I've shared as n times n, and I've associated it to the n and to the n plus 1 terms. What this does is it allows us to simplify, first of all, the n over n terms, and to simplify term by term each of the fractions. So n plus 1 over n is equivalent to 1 plus 1 over n. And 2n plus 1 over n is equivalent to 2 plus 1 over n. So this is, I think, the simplest version of our summation that we can get. And this represents the estimated area between the parabola and the x-axis. It's estimated because for now n represents the number of rectangles we have. This will become a perfect number once we perform a limit. And actually the limit itself is quite easy because 1 over n goes to 0 as n goes to infinity. So the leftover values actually give us an area of 30.667. This should not be a surprising answer because we've done this problem before using 4 rectangles, and we said 26 was an underestimation of the true area. We also found that 34 was an overestimation of the true area. So having 30 and 2/3 seems like a very relevant answer. Moving forward, we're going to use integral notation to symbolize the limit of Riemann sums. So for now, we have been writing the limit as n goes to infinity of the sum of f of xk delta x to represent the area between the function and the x-axis within bounds a to b. In the future, we're going to replace that by this elongated s symbol with bounds a to b, f of x, and dx. That's what we call a definite integral. The symbol, the elongated s, is called the integration symbol. It's a sum, essentially. Dx is what we call the integration element. It's a reminder of the variable being used in the function, and it also can be interpreted as the width of those infinitesimally small rectangles. F of x is called the integrand, and a and b are the bounds of summation, which we presumed were going left to right in this case. So a was left of b. For example, the definite integral from 0 to 2 sine of x dx would actually be a way of representing the area, or stands for the area, between 0 and 2, above the x-axis and below the y equals sine of x curve. So eventually we're going to have to find methods to calculate this area, but the symbolism that is presented above is there to depict exactly that shaded purple region. There's one clarification that will still have to be discussed in the future. If we look at the definite integral, so the limit of Riemann sums applied to sine of x, but over the interval 0 to 4, here is the graph that we would get. This is a situation where the sine function does not remain positive. It actually does dip under the x-axis. So do you think that the outcome will still represent the area between the function and the x-axis? Well, that is left to be seen, and we'll discuss it in a future video.